All right. Hi, John.
Hi.
So let us know, what was the first QIP that you attended?
The first one I attended was in December 1999. It was in Montreal. It was the third QIP.
All right. So all the way back then, when you gave your talks, how did it compare to today? Did you still use slides, or did you use transparencies, chalkboards? What did you do?
Well, most of the speakers actually used these plastic transparencies that we used to write on with pens. But I was a little ahead of the curve. So I actually had a computer. I prepared my talk in PowerPoint. But in those days, you didn't have confidence that the projectors would work. And so what I used to do then, and including in this case, is I printed out all of my slides on those plastic transparencies, just in case I had to use the overhead projector. But I was lucky, and they actually had a working projector, so I was able to plug in my computer.
Nice. Very high tech.
Yeah.
So from your first QIP, roughly how many attendees, or what fraction believed that by now, by 2025, you would have working quantum computers?
By 2025, well, I can't say what the majority thought. But back then, people asked me this question a lot. And for a while, I was saying, well, we're probably 30 years away. And what I meant by that was quantum computers that were fault tolerant and could solve a wide variety of problems. But then I thought, boy, 30 years, that sounds too close. So I started saying 50 years. But then I worried, when you say 50 years, it's the same as saying, I have no idea at all. So I went back to saying 30 years.
Okay.
So by that criterion, by 2030, we should be there.
I see. How are you feeling about that prediction?
Well, I don't think we're going to have scalable, fault-tolerant quantum computers, with 10 to the minus 12 error rates in 2030. We're probably 20 years away from that, but who knows?
Okay. I guess this might already count, but what was a personal prediction of yours from that time that has flopped? If any other prediction, a problem we would have solved by now, or something of that sort?
Well, this isn't really what you're asking, I guess, but our attitude about the modalities for quantum computing has changed. Back then, there was some talk about experimental approaches, but the main things we had were ion traps and also NMR quantum computing using nuclear spins.
Right.
Superconducting was way behind because the coherence times were so terrible, and it took 6 orders of magnitude of improvement over something like 20 years to get to the superconducting qubits we have now.
Okay, nice. In retrospect, which talk from the first QIP attended has been the most impactful?
I think it was mine.
Love the confidence.
So knowing you would ask about this, I looked at my slides. I still have them on my computer. And I was talking about using the Tor code for computation and how to decode it.
Okay.
And I finally wrote a paper about that in 2001. And why it took so long, I can't imagine, because it seemed to all be there in the talk in December 1999. Another thing that I remember being interested in at that QIP was the idea of self-testing quantum equipment, which became the basis of device-independent quantum cryptography protocols, which became very interesting. And here's something else that you're not really asking about, but something that's memorable to me is that I met Peter Shore for coffee in a little coffee shop near our hotel. And we were talking about the security of quantum key distribution, a topic we had discussed when he was visiting Caltech earlier. And that led to our paper, a few months later on security proofs for QKD. So that's one thing that makes it memorable. Can I tell another story?
Of course, go ahead. The stage is yours.
So it turned out I had a postdoc at the time, Michael Nielsen, and I wasn't fully aware that he and his buddy Ike Twong were writing a book. My awareness of that was heightened because they both had laptop computers with them, as did I. Most people weren't traveling with laptops then. But they wanted to share files
Okay.
because they were writing the book, and they were editing each other's stuff. But in those days, there wasn't hotel internet at most hotels, and certainly no wireless.
Right.
So what they did was Ike brought an Ethernet cable.
Mm-hmm.
They were in separate hotel rooms, and it was freezing cold in Montreal in December. And in order to connect their computers, they both opened their windows of their hotel rooms and made repeated attempts to toss the Ethernet cable from Ike's room to Michael's room. And Michael was supposed to catch the cable and pull it into his room and plug in his computer, which after many attempts, they successfully did. And then they were able to share their files.
Wow. The wonders of modern technology. All right, so what is the biggest thing that has changed since your first QIP?
Well, it's much bigger now, of course.
Naturally.
I think there were fewer than 100 people at that one. But another big change is there were no contributed talks. There was no program committee back then. And that was true until the mid-2000s. It was all invited talks.
Okay.
There'd be a program, well, there was a program committee, but they wouldn't review submissions. They would sit around because you couldn't meet on Zoom. I guess maybe they did it on the phone, I don't know. But they talked about, well, who should we invite? It would be interesting to have, and that's how the speakers were chosen.
Okay, invite only, I see.
Right.
All right, what do you think, this might be an interesting one, what do you think would be a plausible plenary title in the 50th QIP that would happen in 2047?
Well, I'm not sure 2047 is the right year, but it would be something like creating universes on a quantum computer. Because I've been interested in a long time, and what can we learn about quantum gravity with quantum simulation? So by then, don't you think we'll be doing that?
Let's hope so.
Yeah.
And finally, a more technical question. In your view, what is the most underappreciated idea in the broader field of quantum information, or within the specific area you focus on?
Well, I'm not sure how to answer that one either, but there is something that comes to mind, which is an idea I like, which I don't think many people know about, although it appeared in a paper in the past year. And that is, for long-distance quantum communication, of course, what we've been talking about for a couple of decades is we need quantum repeaters because of loss in optical fiber or, loss in free space communication. You can't go more than, 100 kilometers or so. So if you want, on a global scale, to have quantum information being communicated, then we need quantum repeaters. But there's another way to send quantum information using vacuum beam guides. There's as far as I know, this idea was suggested by Liang Zhang this year, and then with some collaborators, they wrote a paper. And it's based on the same kind of technology that they use in LIGO. The idea is you have a tube, and it has a high enough vacuum so you can send lots of light through it. And the loss is much lower than in optical fiber, and you could plausibly have a very high bandwidth connection over thousands of kilometers. And my Caltech colleagues think this is cool because they'd like to have a quantum connection between the two LIGO interferometers so that they'd be able to get higher resolution for the signal. And that would be a big project to build that thing. But I think it's underappreciated.
Okay, perfect.
Be able to do it.
Perfect. Thank you so much. Anything else you want to share with the QIP or broader quantum information community?
I hope everybody's having fun because I know I am. And I think the pace of progress in our field is wonderful right now. If you look at the things that have happened in the past year that we're hearing about here at QIP, I just think it's really exciting.
Amazing. John, thank you so much. And we look forward to seeing you at many more QIPs in the future.
Well, I'll be there.